pre-calculus students. Welcome to section 6.3b, directions of vectors and application. So for all of these problems, these are pretty much just example problems because in 6.3a we covered all the notes. I'm gonna keep this toolbox up on the board here, and there will actually be 4 different problems that we are going to try, and so there actually is 2 more after this. So here's what we learned, that the magnitude of a vector is found by taking where the vector is v1 comma v2. If we square v1, square v2, add them up, take the square root, we get the magnitude of that vector, right? Now, to actually find the angle of a vector in standard position, that it is from the positive x-axis, we're talking trig, right, would be inverse tangent of v2 over v1, again, because it's really y over x, just written in vector form. Now, if your v1 is less than 0, meaning it's negative, we're going to add 180 degrees to our answer. You'll see y over here. Or, not both, if theta itself is less than 0, then we're going to add 360 just because the text keeps their answers in with a positive value. Okay. Now, if you have been given a vector, right, it could also be written as v1, the horizontal component, is the magnitude of v times cosine of the angle, right? And we'll see why down here when we draw a picture. And v2, the vertical component, is magnitude times sine of theta. So let's go over to problem number 1 then. How do I find the magnitude and direction, that angle of a vector? And what I've done is given you 4 vectors as written as the sum of unit vectors, right? Meaning this is the vector 2 comma 3, 2 comma negative 3, negative 2 comma 3, and negative 2 comma negative 3. Just written as the sum of unit vectors. So the magnitude then would be, we would square the 2, square the 3, add them up and take the square root. So let's see, that would be 4 plus 9, 13 square root of 13. Okay, now how would we find the angle measure? That angle measure would be inverse tangent of 3 over 2. And I made sure I'm in degree mode. So inverse tangent of 3 divided by 2 is 56.3 degrees. Notice that V1 is positive, so I didn't add 180 degrees. The angle is positive, so I did not add 360. Let's draw a picture and see if that's true. Let's draw this vector in component form. Its initial point is at 0, 0. Right, and its terminal point is at 2, 3. There we go. There's a picture of the vector. Okay, it in fact would be the square root of 13 long, right, about 3 point something, right? And notice it really could have an angle measure here of 56.3. Okay, let's draw the vector 2, negative 3. So 2 and negative 3 would be this vector here that you see. Notice its magnitude would be the same because we would still be squaring 2 and squaring a negative 3, getting a 4 plus 9, square root of 13. In fact, let's take a look. For each of these vectors, wouldn't the magnitude be the square root of 13? And the reason I did that is because we already looked at magnitude in section 6.3a. I'm really focusing on the angle here. So let's find this angle. Inverse tangent of negative 3 over 2. Okay. Inverse tangent of negative 3 over 2 is a negative 56.3 degrees. Now, notice it really does seem to be a negative 56.3 degrees. I will not add 180 because V1 is positive. However, they usually do write the answer as a positive angle measure. So I'm going to add 360 to my angle. It is a coterminal angle. Of course, if I'm at negative 56.3 degrees and I add 360, of course, I'm going to have the same angle. And that angle we will write as 303.7. Okay, again, this angle measure, negative 56.3, perfectly correct, but the book and other texts use a positive angle measure. Let's look at the next vector, negative 2i plus 3j. That would be a negative 2 and a positive 3. There we go. Let's go ahead and get that angle measure. Inverse tangent of 3 over negative 2. Now, notice that we just did that. Our calculator is still going to give us a negative 56.3 degrees. Obviously, we're giving it the same fraction. This vector is obviously not located at negative 56.3 degrees, right? Take a look. Your V1 is negative, and so we have to add 180. So negative 56.3 plus 180, that is 123.7 degrees. Notice that we now have the correct angle measure. That is why we add 180 degrees if V1 is less than 0. Let's go ahead and find this angle measure. Notice that that would be negative 3 over negative 2. Let's go ahead and draw the vector before we put it in the calculator, right? Let's see, negative 2, negative 3. There we go. Notice we've already done this, right? Because your calculator is going to call this inverse tangent of 3/2, a positive. You can put it in, but it's going to give you a 56.3. Notice that that vector is obviously not at 56.3 degrees, but the V1 is negative, so we're going to add 180 degrees to this. So 56.3 plus 180 degrees is 236.3 degrees. Notice that that would be the correct angle measure, and you can see now why it's important to follow these rules. Number 2, how do I write the vector V1, V2 given the magnitude and the angle? It's really simple. Let's do the algebra from the toolbox above. It would be the magnitude times cosine of the angle, our angle being 30 and our magnitude being 5, comma 5 times sine of 30. So super easy. In degree mode in the calculator, I'm going to do 5 cosine of 30, 4.33. I could also use these values from the unit circle, and 5 times sine of 30, 2.5. Okay. So I just want to show you, let's go ahead and draw a vector with a magnitude of 5 and an angle measure of about 30. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1. There we go. So a vector at 30 degrees, so I'm going to make a 30-degree line. There we go. And I am going to make it 5 units long. 1, 2, 3, 4, 5. Here we go. So I used this information here to make this vector, okay? Notice that this terminal point really here, except for my drawing, really could be about a 4.33, 1, 2, 3, 4, 4.33 and a 2.5. Look at that. It really does look like that terminal point. And the reason why this formula works is if I gave you that this length was 5 and asked you for this X and Y when this is 30 degrees, right? You would tell me cosine of 30 is X over 5. And to solve, you would multiply both sides by 5. You would tell me this to find Y, that would be sine of 30 is Y over 5. And you would multiply both sides by 5 to get that side. So that's why it works. Here we go. All right, I'm going to hit pause. I'm going to draw the last 2 problems and we will go from there. Welcome back. So problem number 3, how do I find a resultant vector? Remember we drew some with dashed lines in 6.3 and its magnitude and direction given 2 or more forces. So I have a vector W here and a vector U. We are going to draw a picture. You don't really need to, but it's kind of nice to see your resultant vector is actually accurate. We are going to write these vectors in standard form, which is component form. We're going to add the vectors to have a resultant vector rather than doing that geometrically. We are going to do that algebraically. And then with our resultant vector, we're going to use our formula to find the magnitude and direction of that resultant vector. So take a look here. Let's say you have a 400 Newton force at 30 degrees, maybe pulling on a tree stump, something like that. So I'm going to make a 30-degree line about, and I'm going to make it 4 units long. So I'm going to make each unit that you see here 100 newtons. There we go. Okay, and so I'll just, on my vector 1, 2, 3, 4. There we go. There. So I tried to draw a picture semi-accurately of vector W here. Notice that vector U is 300 newtons, but at a 70-degree angle. So that is pretty steep. And it is only 3 units long. So 1, 2, 3. There we go. And here is vector U. Okay, let's go ahead and let's write our vectors in standard form. Vector W is 400 is the magnitude, cosine of 30, comma 400 sine of 30, plus vector U is 300 cosine of 70 and 300 sine of 70. And I'm going to add these together. So here we go. I am going to, in my calculator, in degree mode, put 400 cosine of 30. I'm hitting enter, and I'm going to add that to 300 cosine of 70, right? I'm adding the horizontal components together and putting them in the horizontal position, and then I'll add the vertical components together and put them in the vertical position. And I get 449.016. Okay, same for vertical. I have 400 sine of 30 plus 300 sine of 70. And I get 481.908 is that vector. Now, first of all, let's go ahead and draw this, right? This is about then 4.5 units, right? So I'm going to draw this vector with a terminal point of about 450 and 481, right? So 450 and 481. So 450 right here in 481, about right here. Let's take a look. There we go. Is it possible that if you added these two forces in these directions together, that you might get this vector here? I think so, right? They're working in the same direction quite a bit, okay? Notice that if we had added these vectors, if these vectors were going exactly in the same direction, right? All their forces were working in the same direction, that would be 700 newtons, right? So, but they are working slightly against each other. So let's do the magnitude. I'm going to square 449.016, 481.908. I'm going to add them up and take the square root, and that is going to be our magnitude. Okay, so let's see, square root of 449.016 squared plus 481.908 squared. There we go. That's a magnitude of 658.673 newtons. Again, notice that makes sense, right? If they were working together, it would have been 700. So you can see why 658 would work. Notice this would be about 6.5 units. And if I drew along here, I am betting it would be about 6.5 units long. Let's get that angle measured. That is inverse tangent of 481.908, right? V2 over V1. From the picture, it looks to me like that, if my drawing is semi-accurate, around 50, 60 seems to be the angle measure. Let's do that. Inverse tangent, 481.908 divided by 449.016. That angle measure 47 degrees. 47 degrees, close to 50. 47 degrees, right? And you can see from the picture, it about is, right? So that's pretty cool, I think. Last problem. How do you find a magnitude in an angle that puts a force in equilibrium? And honestly, all you do is you keep the magnitude the same, right? If I am going at a certain force in a certain direction, to put me into equilibrium, to stop me, the force has to be equal, but in the opposite direction, right? 180 degrees. So let's say that my magnitude is a velocity of, let's say 20 feet per second, right? And I'm going in a direction of 30 degrees. That would mean to put me in equilibrium, someone would have to apply 20 feet, a force of 20 feet per second in the opposite direction, which I would add 180 that in a 210 degree direction. And that would stop me, right? Set me at zero. So I hope you enjoyed section 6.3b. I hope you have an amazing day.